This is the first part of the lecture on section 5.4 on eigenvectors and linear transformations. There is a live class video posted about this section, but the classroom video starts about halfway through the handout. So what I'm going to do here is I'm just going to get the handout started, get through the first few pages, and then you can watch the rest of the discussion in that live classroom video. So we're going to start out with 5.4 with a couple exercises, and they're on the first page of this sheet. And I wrote this little note, I squeezed it in on the side of the handout, you'll see. Just note, these two exercises do not involve square matrices. The entire rest of our Chapter 5 material always involves square matrices. So this is sort of a little side journey away from square situations. And as soon as we finish these two examples, we go right back to the square situation, which for the rest of this section. So let's get started here and let's look at these examples. So let E be the set of E1, E2, E3, 4 be the standard basis for R4. So I'm talking about four-dimensional space. And let V be a vector space with a basis B1, B2, B3. So we're thinking of V as some abstract vector space. It's got a basis with three vectors, so we know the dimension of V is 3, but that's about all we know about V. It's some abstract space that's three-dimensional, and we have a basis for it. And I'm saying let T be a linear transformation with the following property. So it's given that T is a linear transformation. We do not have to verify this. And here's what T does. T takes a four-component vector, so it takes a vector from R4, and assigns it to a linear combination of B1 and B2, B3, the basis for the vector space V, according to this formula, right? x1 minus 2x3 B1 plus x1 plus x2 plus x3 B3 B3. All right. And what I'm asking you to do is find a matrix for T relative to the bases E and B. Now this is not a hard math problem. This is really just interpretation and notation and trying to get you used to the way we use our language and notation when we're working with an abstract vector space. So what we want to do to find this matrix is I really want to think about what T does to the basis vectors of R4. So I'm going to look at T of E1 to start out with. That's just T of the 1, 0, 0, 0 vector. And so if x1 is 1 and 2, 3, and 4, x2, 3, 4 are all 0, what am I going to get? Well, I'm going to get 1 minus 0 B1, so I get 1 B1. I'm going to get 1 plus 0 B2, or plus 1 B2. And I'm going to get 0 B3, right? So I don't have to write that, I'll just write B1 plus B2. And let's do this with each basis vector from R4. Let's see, so T of E2 is going to be B2 plus 2B3. T of E3, T of 0, 0, 1, 0. So only x3 is 1, the others are 0, so I think I get minus 2b1 plus b2, and I think that's it. And then T of E4 is T of 0, 0, 0, 1, which is going to be let's see, we only see x4 here, so 3b3. Okay. All right, now what we're going to do is we're going to translate b1 plus b2, each one of these expressions on the right, into a vector form where we're going to think of these output vectors in the form, let me see if I can just write it here, b1, b2, sorry, I don't mean b1, b2, b3, I mean coefficient of b1, the coefficient of b2, and the coefficient of b3. Maybe I'm better off just writing it down here. So the coefficient of b1 is 1, a b2 is 1, a b3 is 0. So I get 1, 1, 0. It's kind of obvious what I'm doing here. 0, b1 plus 1, b2 plus 2, b3. So we're just turning these into column vectors that correspond to elements of this abstract vector space, even though the abstract vector space V is not actually R3, minus 2, 1, 0, 0, 0, 3. And so really all this problem turns out to be is writing these 4 columns in a row, I'm sorry, these 4 columns next to each other to create a matrix, 1, 1, 0, 0, 1, 2, negative 2, 1, 0, 0, 0, 3. And that's what we call the matrix for T relative to these bases. So this is what we're after in this problem. But I just want to give you a little bit more notation here so you can be more comfortable too with some of the book's notation. So what we would say is this is the image, so T of E1, right? T of E1 with coordinates according to the basis B. So a different basis for the vector space V would give us different 3-component column vectors. These entries depend on the fact that we had chosen a particular basis for that vector space V, and we don't know what those actual basis vectors are. We don't even know what the elements of V are. Okay, so and down the line, this is T of E2, coordinates in B, T of E3, coordinates in B, T of E4, coordinates in B, and we can think of this matrix as being, what would we do with it? Well, we're going to take 1, 1, 0, 0, 1, 2, negative 2, 1, 0, 0, 0, 3. And we would multiply by x1, x2, x3, x4, a vector in R4. Now I would call this the vector x expressed in E coordinates. And after we carry out this multiplication, we're going to get a 3-component vector. And I'm just going to write 3 spaces here. I don't want to fill in. Really, we're just going to get the rule for what the outputs would be. And this, we would say, is the image of x, so T of x with coordinates in the basis B. So a little kind of excess of notation here, but just I think that's it. That's all I want to say about this one. Let's go on to the next exercise. Okay, so the second exercise on this sheet is another linear transformation situation. First, I just say it's a mapping, so we're just saying it's a function. We don't know it's a linear transformation yet. From what we're calling P3 to R3. P3 is that set of polynomials of degree less than or equal to 3. And R3, of course, is our usual three-dimensional Euclidean space. And what t does is, the function t does, it takes a polynomial, so little p here is some element of P3, and it assigns it this vector in R3. It evaluates the polynomial at 0 to get a number. That's the first component. Evaluates the polynomial at 2 to get the second component. Evaluates the polynomial at -1 to get the third component. Okay. So let's do the 3 parts of this problem. Let p of t equal t cubed minus t squared plus 1. Find the value of t of p, the transformation applied to p. Well, we need to figure out what p of 0 is. P of 0 is 0 minus 0 plus 1 is 1. P of 2 is going to be 2 cubed minus 2 squared plus 1. That's 8 minus 4 is 4 plus 1 is 5. And p of -1, plugging into this polynomial, is -1 cubed minus -1 squared plus 1. And so I think I'm going to get -1 minus 2 plus 1 is -1. So I think t of p is going to be 1, 5, -1. So there's the answer to part A. Part B is to show that t is a linear transformation. And to do that, we got to verify 2 properties. It's a little bit tedious. We got to show that t of the sum of 2 vectors is equal to the sum of what we get when we apply t to those vectors separately. And t to a scalar multiple of a vector is the same as what we get when we take the scalar multiple times t applied to that vector. Again, the vectors here are elements of P3, so they're polynomials of degree less than or equal to 3. So now I can choose my notation to use here. I'm just going to let P and Q be polynomials in this capital P3 space. So they're not polynomials of degree less than or equal to 3. So this P has no connection to the P in part A. I hope that's okay. I could have said P sub 1, P sub 2. Then I got to copy a whole bunch of subscripts along the way. All right. So what we need to check is, what is T of P plus Q? T of P plus Q is going to be, thinking of that as a new function, the sum of those two. It's P plus Q evaluated at 0. It's the sum P plus Q evaluated at 2 in the second component. It's the sum P plus Q evaluated at -1 in the third component. And this is going to work because when you add 2 polynomials and evaluate them at a number, you get exactly the same thing if you had evaluated the polynomials separately and then added the values that you get, right? So it's like nothing much going on here at all. And now as column vectors in R3, we can say this is P of 0, P of 2, P of -1, plus Q of 0, Q of 2, Q of -1, which is T of P plus t of q. And we got our first requirement for being a linear transformation satisfied. So, for functions in general, having this kind of property satisfied would be very unusual, but it's required for a linear transformation. Now let C be a scalar, so just real number. Look at T of C of P. T of C of P is going to be C times P at 0, C times P evaluated at 2, C times P evaluated at -1. And because we have a column vector here, I can factor out that scalar C and write what I have this way, which is C times the value under T of P itself. So that's all there is to verifying the scalar multiplication condition for a linear transformation. Therefore, T is a linear transformation. Okay, so we got part B of our problem solved. Now, let's talk about part C, where I'll scoot that up a little further. Find the matrix of T relative to the basis 1t, t squared, t cubed. So the basis 1t, t squared, t cubed of P3, and the standard basis of R3, which we know is 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay. Right. So what we want to do is kind of like in the previous problem. We want to look at T at each one of these basis elements of P3. So we're putting in here the domain is P3, so we're taking its basis elements and applying the linear transformation T to it. And now, what are we going to get? So what is 1? 1 is just the polynomial. You could call it 0t cubed plus 0t squared plus 0t plus 1. Just like t is 0t cubed plus 0t squared plus 1t plus 0. So each element of P can be described as having 4 terms, but sometimes these coefficients are 0. And for these basis vectors, the coefficients are either 0 or 1. And so t cubed is 1t cubed plus 0t squared plus 0t plus 0. And so what I got to do now is I'm going to get this column vector where in the first component I'm going to evaluate the polynomial when t is equal to 0. Well, if I plug t equals 0 into 0t cubed, 0t squared plus 0t plus 1, I get 1. If I plug in 2, if I try to take p of 2, if I plug in t equals 2, I get 1. If I plug in -1 for t, I get 1, because this is just the constant polynomial. You get the value 1 no matter what value of t you plug in. For this second one, at 0, now again, all I'm going to get is t, right? So when I plug in t equals 0, I get 0. When I plug in t equals 2, I just get 1 times 2 is 2. When I plug in t equals -1, I just get -1. and so on and so forth. So for the next one, when I plug in t equals 0, I get 0. When I plug in t equals 2, I'm going to have 2 squared here, so 4. When I plug in t equals -1, -1 squared is 1, so I get 1 times 1 is 1. And can I squeeze my fourth one in here? When I plug in t equals 0, I get 0. T equals 2, I'm just going to have 2 cubed, which is 8. When I plug in t equals -1, I'm going to have -1 cubed, which is -1. Okay. Now, again, that really all you got to write down then is a matrix having these columns: 1, 1, 1, 0, 2, -1, 0, 4, 1, 0, 8, -1, and I want to just say a little bit more about the notation used here. So that's actually the answer. That's the matrix we're after. We'd be done if we just wrote that down. But I know this polynomial space drives people crazy, so I just want to give it a little bit notation. If I wanted to take, if I call this basis B, so let's just use the letter B for this basis of P3, so it has a name. If I were to take any polynomial in P3, and I use this notation, what are its B coordinates? Well, P of t, which is like, say it's P of 3 t cubed plus P of 2 t squared plus P sub 1 t plus P0. And this is where P3, P2, P1, P0 are scalars, are real numbers, okay, just coefficients of those polynomials. This vector in B coordinates we could just write as P0, P1, P2, P3. Now, we had to make a choice on who goes first, so this is assuming that 1 in B coordinates is 1, 0, 0, 0. T in B coordinates is 0, 1, 0, 0. T squared in B coordinates is 0, 0, 1, 0. And T cubed in B coordinates is 0, 0, 0, 1. Okay. And why did I go in order from P0 to P3? Why did I start with the constant coefficient, work my way up? There's really no rule here. I could have gone in either direction as long as I'm consistent. And actually, this ordering of the columns in our matrix really matches this ordering of the coefficients of the polynomial. So it's really just a question of being consistent. You could do everything in the reverse order, or any order really, as long as you were consistent in the whole scheme of things. So the one last thing I wanted to add here is to just take this matrix and what we could multiply by is A0, A1, A2, A3, which I would call a polynomial p in b coordinates. And what we're going to get after we multiply that out is a0. We're going to get a0 plus 2, a1 plus 4, a2 plus 8, a3, and then we're going to get a0 minus a1 plus a2 minus a3. So I just multiplied matrices there. This can be thought of as the image of the polynomial p under that linear transformation. That's the image in the standard basis of R3. So what's this weird formula I wrote down? Well, this is just p of 0 for any polynomial as a constant coefficient. This is just p of 2 for any polynomial. If I plugged in 2, I would get this linear combination of the coefficients. And then this is just p of negative 1. So p of 0. There's p of 2. There's p of negative 1. So, okay, I got kind of carried away talking about this thing, but I just wanted a chance to give you a little bit more sense of what's going on with the abstraction of this problem, where here's the part C of that exercise from here. Really, at this point, we already got our answer. Everything I've written after this is just extra stuff to give you to contemplate. So there's going to be a little bit more of extra content because I got to talk about the next 2 pages of the handout, and we'll do that next.